Workshop on using the statistical programming language R. My name is Rick Henson. I'm one of the 5 speakers, and this is a reminder of the lineup this morning. Simon will start with an introduction to R, sort of basic syntax and philosophy. Athanasia will then talk about visualization in R. Didier will talk about some basic univariate stats. Rogier will then talk about multivariate statistics. And then finally, I'll say a few words about Bayesian stats. Just to remind you that this session is being recorded, so don't worry if you miss a bit or didn't hear something, because you can always rewind and replay afterwards at your heart's delight. We would welcome questions throughout. The best way, well, the only way to ask those questions is to go to the bottom right of your screen, where you can see a box for live chat, and so you can discuss amongst yourselves if you wish. And there's also a second tab for questions. And if you type your questions in there at any point, at the end of each talk, the speaker will try to address as many as possible. Each speaker will talk for about 20 minutes, and then we have about 5-10 minutes between talks to try and answer your questions. The questions are all anonymous, and so please don't feel inhibited. Please do ask away. And you might find it helpful to go to full screen mode while you're watching this, particularly for some of the font size for the live demo that we'll be doing in RStudio. And finally, just to remind you, there is an OSF website where you can download all the material that we're using today. The link is on the bottom of the screen. The link is also now on the workshop tab on the BNA Festival website, if you want to try running some of the code that we'll demo today. That's it from me. So now I'll hand you over to our first speaker, who is Simon White at the MRC Biostatistics Unit in Cambridge. I can't hear you, Simon. You don't know if you're muted.
Sorry, let's try that again. Morning, everyone. So I'm Simon, and I'm going to open this session with an introduction to R. And so hopefully my screen is live, and you can see that I'm going to demonstrate this in something called RStudio. So RStudio is just an environment in which you can interact with R. So the aim of this opening session is to essentially go through the language of R. So what the terms are, how you understand what the bits and pieces of using the statistical language are. So this will help you understand the next few talks. The other really important part of this talk is that after we finish this session and you start to use and learn R yourself, when you have a problem and you go and Google for an answer, you know what words to put into the search bar. So with that in mind, I'll crack on and I'll leave some time at the end for some questions. So I'm going to go through several topics at quite a high level. So the first thing is, what's the fundamental thing we work with in R? Well, you only need to understand two things, functions and objects. And as a bit of a spoiler, functions are actually just a special type of object. So really, there's just objects in R. So this is going to be a very short introduction. Objects have a name, and so they have names that are lowercase and uppercase letters with numbers or dots. And if we just had objects, R would be very boring. So objects have a type, or the phrase we use in R is a class. So you have different classes of objects. And you have the normal ones you'd expect, so numeric, logical, integers, and then you start to get structures, so data structures like matrices and data frames. But you also get more exotic objects. So a MER-mod object is the output you get when you fit a mixed effects model. So they're just objects in R. So as I mentioned, I'm doing this in RStudio, which is an environment that lets you interact with R. So on the left here, I've got a script, which you all should have access to, and you can follow through at your own time. At the top right here, this is R. So you can send commands from your script to R, and they appear in the corner. The first thing to know about R is, unless you save something, it's lost. So although I've got the answer 6 for 4 plus 2, it's vanished, and I can't do anything more with it. So what we have to do in R is assign things to objects. And we do that with the assignment operator, also known as the arrow operator, which is these two characters specifically together without a space in between. And when you make assignments, you see that nothing happens in R, so assignments happen silently, but in RStudio down here, I've got a list of the objects I've now made in my environment. So now I can do Alice plus Bob, because Alice is just the number 4 and Bob is the number 2. So we have objects that represent things and we can work with them. Now again, the number 6 has been lost, so unless I save it, it's gone. So this is an important idea when working with R, is that essentially everything you do, if you want to use it again, you need to assign it to an object. So what about functions? So if we only had objects, the world would be very boring. So what we want to do with an object is do something with it, and that's a function. So a function is something we do to an object. So here I've got the function square root. So that's the square root of 4, which is definitely 2. And so you know there are functions because they have round brackets or parentheses. So a common error new people to R make is they don't get their brackets right. So if you forget your brackets, if you come from other languages or Stata or something like that, you might get an error like this, and that's because you've forgotten the brackets. The brackets tell R it's a function. That's another reason why we recommend something like RStudio, because RStudio, when you're writing scripts in the top left, it helps you balance your brackets and it tells you if there's something wrong with the brackets. So because there are only objects in R, what happens if you ask R to do something silly? So here I'm asking R to take the square root of a string called hello. So I know it's a string because it's in double quotes. So that would be like names or ID numbers. But the square root of hello doesn't make any sense. Oh, sorry, I've just run hello. That does make sense. The square root of hello doesn't make any sense. And this gets you to one of the challenges of learning R is that sometimes the error messages aren't particularly informative. So the error message here is that we've just got a non-numeric argument to a mathematical function, which is easy to spot in this instance, but sometimes those errors are, I don't quite know what's gone wrong. But the important thing is that we have functions and objects, and you can apply functions to objects. So we take the square root of Alice, remembering that Alice is just an object that holds the number 4, so we get 2. At which point you've got the basics of how you interact with R. So what's going to follow now is how do we make that more interesting? So the first thing is functions can take multiple arguments. So the arguments to a function are separated by a comma. So here I've got a function called sequence, which has 1, 10. So it's got 2 arguments, 1 and 10, and that makes a sequence from 1 to 10. And then in this line, I've now added a third argument, 2. So what does that do? It does a sequence from 1 to 10 in steps of 2. And this brings up an important point, is that up in this first line, how did R know that I wanted the sequence in steps of 1? I didn't tell it that. There's a default for that argument. So when you come to use functions in R, you don't have to specify all the arguments. Some of them will have defaults. And it's important to then read the help files so that you know, and so this will make the help file appear in the bottom right, what the defaults to those arguments are and how they work. So it's fine not to specify an argument, but you should make sure, particularly when you're doing the statistical functions, what are the defaults? The other really important thing about arguments is that they have names. Nearly all of them have names. And as a beginner, I would strongly recommend to write the names of the names of the arguments to the function. So you write the name and then an equal sign and then what you want the value of that argument to be. The important thing is if you name arguments, the order doesn't matter. So sequence from 1 to 10 is the same as sequence to 10 from 1. Whereas if you don't name the arguments, the order does matter. So sequence 10.1 goes the other way. So this can be particularly in the, again, so the more statistical fitting functions that can have 8 or 9 arguments. If you don't name them and when you type your script, you put 2 of them in the wrong order, weird things will happen. It might take you a long time to work out why. So personally, I would always name your arguments. So putting that together, all those sequences above have been lost. So I'm going to save that sequence to a function called echo, an object called echo, and then I'm going to apply the function log to echo. That's the natural logarithm. And then we get on to a function called plot, which does exactly what you expect. It makes a plot. And that, when you're working in RStudio, will appear in the bottom right. Now, I'm not going to talk about visualization. That's the next speaker. But a lot of making pretty graphics and visualizations in R is finding the right function and then setting the right arguments. So you can change the arguments. So I've made it into a plot of points, and I've put a title on, and you can do all sorts of things to the axes. So when you are so the reason I focus on the sequence function is that making sequences is a really common thing to do. It's so common that because of the inherent laziness of humans, they made a shortcut, and that's called the colon operator. So the colon operator is essentially just a shortcut. So those 2 lines are exactly the same thing. And that's just because you write sequences so often. So, pardon me. So something you'll see a lot of when you go online and you Google for R scripts is something that looks like this, which is 1:length and then the name of an object. So length is a function that just returns the length of the object. And that brings me on nicely to what is, I would argue, the most commonly used function in R, and that's the C function. So you know it's a function because it has open and close brackets, parentheses, and it's got arguments separated by commas. And you know it's used a lot because, remember, we're inherently lazy, so if we have to type it a lot, it's good to make the name of it short. So C is actually short for concatenate or combine. So what the C function does is all of its arguments, it bolts them together into one object. So that line just makes an object called hot, which is now a numeric vector. So we've now got into this idea that objects can contain data structures, so lots of things. So this brings us on nicely to one of the most common data structures, which is a data frame. So in R, a data frame is essentially the way you might think of it as an Excel spreadsheet. So it has rows and columns, and the columns can hold different types of data. So you could have a column of ages, a column of dates, a column of sex, male, female. So it's a data structure, but it's all in one object. So I'm going to use one of the built-in data objects called faithful, which we use the function class, which no prizes tells you what class an object is. So that's a data frame. Faithful happens to be a data set about eruption times from Old Faithful in Yellowstone National Park. It's a really cliched teaching example. We're going to do some more relevant examples later in the workshop. But you'll see the first thing is that when you type an object, it prints it out here, but it's gone off the top because there are 272 rows. So I'm going to quickly introduce you to a function called head, which just looks at the top rows. And then just to call back to my previous section, why has it picked 6 rows? Because that's the default. There's an argument that you can tell it to pick out how many rows you want. So we can look at class of echo. Remember, that was our numeric vector, and that's a numeric vector. What's the class of square root? Well, square root is a function. It's a function. So that's all well and good. So we now have functions we can apply to objects, but what if you don't want to apply your function to the whole object? What if you want to pick out a part of an object? And so now if we have a data frame, we've got rows and columns, you might want to only work with certain rows or certain columns. So that's where you want to extract parts of an object. And that's the square bracket notation. So you put square brackets. So exactly the same with the parentheses, you have to have an open and a closed square bracket. But that tells you want to pull something out from inside an object. So here we're picking out the second element of echo or the 100th element of echo. And so echo is that sequence of numbers we've generated earlier. And remember, just because everything in R is an object, we can extract inside the square brackets using an object. So we can pick out the Bob elements of echo. Bob, remember, is just the number 2. So that picks out the second element of echo. So when we come to data frames, we've got rows and columns. So that means we need to give 2 indices, a row and a column. So you'd have faithful 1, 1 inside the square brackets is the first row, first column. And something you'll see quite often is if you omit a dimension, so you don't put anything, R interprets that to mean all of them. So 1, nothing means give me the first row and all the columns. So we can see that that returns this in the console. So that's that's the first row of data. And likewise for the columns. And this brings me on to a usability point. This is terrible code. It makes no sense in 6 months' time. Which one is column 1? You won't really remember. And it's very liable to introduce bugs and errors in your code. So thankfully, we can get around that because the columns of our data frame have names. They're called eruptions and weighting. And you can access that with a function called colnames, which tells you the name of the columns. Logically, there's also a function called row names. So in some data frames, you might have the rows might have names, and you can access the rows by name as well. So the important thing is that then we can, inside our square bracket notation, we can use the names, and now they're names because they're strings, so they have to be in double quotes. So anything inside double quotes is a string, and so we use the names of the columns as strings to pull out the things we want. So that, I would argue, is much more readable. And in 6 months' time, you'll instantly look at that line and know what it does. So just some common mistakes when you're subsetting. You might do echo 1, 2. That's an error because R thinks it's got rows and columns, but it doesn't. What you meant is to wrap it inside the C function, which is why I'd argue the C function is one of the most used functions in R. Another common mistake is from the faithful data frame, you might say, I want the weighting column and the first column. So you'll do something like that, and you'll get an error that says there's an undefined column. And you go, oh, what does that mean? And so it turns out that, remember, everything you can break down to smaller parts. So let's go to the innermost part, so the concatenate function. The problem is inside the C function, you can only bolt together things of the same type. So when we bolt together the number 1 and the string weighting, R silently turned the number 1 into the string 1. And so then it was looking for a column called 1, and there wasn't a column called 1. So if you find an undefined column selected error, you might have accidentally turned numbers into strings somewhere. So there's a place where R gives you an error where it's surprising. This you might expect would give you an error. So what's the 2.1 element of echo? R gives you a number back, which might surprise you because you thought that would give you an error. Silently, R has turned the 2.1 into a 2 using the floor function. So sometimes R gives you errors and sometimes it silently converts things. So this can trip you up when you're learning R. So you just have to be careful of those things. So inside objects, the key thing is that objects organize your data into structures. So when you make new derived variables, you want to keep it inside that object. So you can just add things to objects. So faithful at the moment is just 2 columns. If you derive something, so here I've got some mathematical function of those 2 columns. Well, at the moment that's lost, but I want to save it. Well, the best place to save it would be in the faithful data frame and as a new column. And so you can just assign to a new column. So that doesn't exist. And after I run that line, it now does exist. And so you can see I've kept this calculation of density, or whatever you want to do, has been added as a new column to this data frame. So that makes it much easier to keep your data coherent and well ordered. At this point, something you'll come across a lot in R scripts and online is something called the dollar notation. So the dollar notation is a way to access columns inside data frames. Now, essentially, you write the name of the data frame, a $, and then the name of the column. So this will pull out the eruptions column. Now, the benefit of the dollar notation is that you don't have to write the full name of the column, so you can abbreviate. So if you've got long column names, you can just type faithful E, and that does the same thing. If you use the subset notation with the square brackets, that doesn't work because you've got an error because there is no column called E. So the dollar notation, born of human laziness, exists. However, I would warn there's a slight issue with it in that E was unique. If I add a new column called errors, and now I try faithful $E, I get an error. So bizarrely, what did work now doesn't work. And that's because $E is no longer unique. So R can't uniquely find a column. And this is an error I see a lot of new people to R make when they start using the dollar notation and abbreviate columns, particularly if you abbreviate a column to a single letter and then you later add a new column. You'll then try and run your code and it will break and you will spend a long time wondering why. So special values. So inside R has the special value NA. Now, NA is R's magic missing value. So it's a capital N, capital A, and it's not a string, so it's not in double quotes. It is a value. And this would be the equivalent in other computing languages or software. How do you code a missing value? So sometimes people code this as sort of like minus 9,999 or -1 or infinity or something like that. R has a special value to indicate missingness. And the nice thing about missingness is that it propagates. So what is 3 plus I don't know? The answer is I don't know. What's the square root of I don't know? I don't know. And so in a lot of R functions, they have arguments about how to handle missingness. So if you're working with survey data or even imaging data where you might have voxels that have dropped out for a subject, so they're NA values, you need to work out what you want R to explicitly do with the NAs, because if you don't tell it, the answer will probably be NA. So here, what's the mean of the moon vector? I don't know, because there are missing values. So you can tell R to take the mean of only the non-NA values. So quite often, sometimes you might run a complicated analysis and the answer will pop out as NA, and you'll go, well, that's not very helpful. And probably because somewhere in your data set, something you're trying to calculate includes NAs. So we've talked about taking out parts of objects. Obviously, you might want to take out parts of objects conditional on something. So you have all of the standard comparators you would expect. So you can do equals to, less than. So, A is less than B alphabetically, that's true. 3 is less than 1, no, that's not true. So you get trues and falses. So you can do all of the standard comparators. One thing that brings me on to then is in R, there's sort of a slight separation. Do you want the things back or the indices of the things? So this is easier with an example. So we'll make a new numerical vector dark. So we can apply the sort function, which sorts the dark vector and returns the actual numbers, or you can use the order function that returns the indices ordered. So in dark, which is the smallest element, it's the second element. So you can see that here. So the second element was 2. In dark, which is the biggest element, it's number 3, and that's 44. So just when you're using functions in R, you just have to be careful. Do you want the things back or the indices back? And particularly when you're using the square bracket notation to subset, that can trip people up. So just another example here, you've got a vector of planets, which includes Pluto. So the grep function searches within those strings for that substring AR. So grep by default just gives you the indices. You can say value equals true, and that will give you the values back. Or you can use a function called grep_l, which will give you a logical. And which one of those three you want depends on what you want to do with it. So the final conceptual thing I need to talk about in R is factors. And this really goes back to the use of human readable names. So factors are R's way of assigning human readable labels to categorical variables. So I'll just give a quick example here. So I've loaded a new data set called air quality, and in that there is a column called month. And that is just, as we can see, a column of integers. So this is a bit of a spurious example because obviously we all know what the 5th month is, that's May. But if the kind of example you see this is you'll get a data set and have a column called sex, and they'll be coded as 1 and 2 or 0 and 1, and you'll be like, well, which one's which? That I don't know. So this is the way that R works to fix that problem. So you create factors using the factor function. Remember, everything is just functions applied to objects. And you give those numerical integer values that represent the categories, you give them human readable names. And months is such a common one that there's a built-in object with the names of the months abbreviated. But I've made a new column called month all capitals. So capitalization matters in R, so lowercase and uppercase are different. But all caps month is a factor. So now when we look in the data frame, there's this new column month, and it's got a May. The real place this helps, and I find it makes your code more readable, is when you start in comparators and extracting parts of objects. So here, air quality, which elements of air quality month are 5, that's all right for month. But if that was sex equals 1, you come back in 6 months' time, you go, well, is male 1 or is female 1? Which one was 1? So the second version, where you can now say, well, is it equal to May, I would argue is a much more readable way of writing that code. And it will help you a lot, particularly in more complicated situations. And then you have a whole series of other functions that let you work with factors and access parts of the factor. So how many levels of the factor, how many levels of the category are there? So I'm not going to talk about the formula interface. My next speakers are going to mention this more. The formula interface is essentially a really powerful tool in R. The primary thing is that you have a function with an argument called data, and you give a data frame as that argument, and then you write a formula in terms of only the column names. What the formula means depends entirely on what the function is. So the LM function here fits a linear model. Remembering that I've just run that linear model and I've lost the output because I didn't save it anywhere, but that would fit a linear model of the type you would imagine. But people will talk more about the formula interface later, but it's a very convenient tool in R. So the final two things, base R is what you generally install straight away, but there's lots of extensions. So R has been extended to do lots of different types of analyses. The R website has lists of packages or libraries. We use the word package and library kind of interchangeably, which extend R. So these are two packages which fit random effects models. They're slightly different. If you need to know why, you need to, I mean, one fits nonlinear random effects and the other one's mainly linear random effects. This is a package that in R extends it to allow it to fit structural equation models, which is a popular one to use. And there are lots of packages, and some packages have entire books written about them. So you find what you need and then have to do some further reading online. The main thing that's probably most important when you first start is how do you get your data into R? We're not going to talk about data cleaning and data management. That's an entire day's school on its own. But the key thing is that there are the standard functions you might expect to read in CSV or comma-separated value files. However, if you have your data in an existing form already, so if you're coming from MATLAB or SPSS or something, or you've got your data in Excel, there are libraries that allow you to directly read those files. So you can just directly pull those data sets in. And likewise, if you have your data in a database, you can access it directly from R, which makes everything a lot easier. So at that point, I'm going to stop sharing my screen. And
thank you, Simon. Very clear. We don't seem to have any questions come through yet. There might be a slight delay as they come from Swapcard to StreamYard. Okay, there are no questions, but thank you. That was really clear. So we'll move on to the next speaker, which is Mo, who works at the University of Oslo. Thank you, Mo, for taking part, and over to you.
Thanks. Okay, so thank you for inviting me, and Simon, that was really cool. There were actually a couple of things in there I didn't know, like the $sign column abbreviation. I've never seen that. I love the $sign. I use it all the time, but I always write the full column name. So I didn't know it could abbreviate, and definitely can see that turning into issues if you do. So don't do that. So yeah, so I will be talking about data visualization, and I will be mainly using a package, like Simon mentioned a little bit later in his talk. I will be using a specific package to make plots, and I will start sharing my screen so you can see what I'm doing. Hopefully everyone can see my screen, and that looks fine. So just need to rearrange my own screens a little bit here. There we go. That's better. So yeah, I will be talking about a package called ggplot2. I will tell you why very shortly. I just wanted to do like my own self-promotion because I'm trying to get comfortable doing that. I have a PhD in cognitive psychology, so I learned coding during my PhD. I have no formal training in it. If I could learn it, so can you. So let's do this together. Find me on Twitter. I'm very happy to engage with everyone. If you have questions and you don't dare share them here, share them with me on Twitter, and I will answer when I can. I'm also part of the LifeBrain EU project together with Rick and Roger, who are part of this workshop as well. So, okay, so graphic systems in R. In my opinion, there are like 5 basic, not basic, definitely not basic, but there are 5 graphic systems in R that you can use. It's the base R plotting system, which Simon briefly showed, like with the plot function, which is great for very quick and easy visualizations, and you don't need extra packages. It works out of the box. It is really nice. Then you have Plotly and R2D3, which are actually based on JavaScript, but you can call them through R without needing to deal with JavaScript at all. So that's pretty nice. And they make really nice and flexible visualizations. And then there's the Lattice package, which I have no experience with, but I do see a lot of people like it and use it. My personal preference is ggplot2. And GG stands for Grammar of Graphics, and it's this like very opinionated way of creating graphics, and it's quite different from a lot of other graphics packages. So it does take a little bit of time to get into, but once you kind of understand the logic of it, it is extremely flexible, and you can make some really, really nice plots with it. And as like a quick overview, so everything that has parentheses after it on this slide is a function in R, or is a stand-in for a function in R. And ggplot2 has lots of different components. You always start the call with the ggplot function, and then you can add to that ggplot function lots of other components, which are other functions. You add geoms, which are geometries, which can be like you want to make a point plot, you want to make a line plot, you want to make a histogram. So that kind of decides what type of plot you're making. You can scale the color or the X or the Y axes, for instance, to kind of fit what you're after. You have the coord functions, which alter the coordinate system or zoom in and out of your plot where you want it to go. You have the themes that alter kind of the general aesthetic of the plot, like what color the background is, what color the text is, and stuff like that. You have the labs function, which I use a lot, which alter the names of, for instance, the x-axis or the y-axis or the name of the color. We're going to show what that means. It has a somewhat overlap with some of the scale functions, so be a little bit aware of that if you use both of them. And then you have facets that create kind of subplots or a grid of plots based on like your main plotting function. So all of this is like too much information. You've already lost what I'm talking about, but I will break it down, and I promise that you will be able to follow me at some point. But before I continue, I just want to talk a little bit about two very key concepts of ggplot2. And that is the difference between mapping and setting. So when I talk about setting, it means that I'm setting a single value for all of the data. Like I want all my points in my scatter plot to be black. And then I say color equals black in quotation marks, and all of my points will be black. That is setting an aesthetic value to like one thing. When I talk about mapping, it means that I want something to vary. And I usually want it to vary over some logic of my data that I'm giving ggplot. Like I want color to map to a column in my data called groups, so that the different groups I have get distinct colors for their plots, for their points. So it's easy for me to see which points correspond to which groups. So that's mapping. So you map a variable to the data set you're giving ggplot so that it can vary over time. So this is a key concept, and I'll keep using these two words all the time, hopefully to get it kind of ingrained into you, because you will see this concept a lot if you start Googling ggplot2. Okay, so as I said, base R plots are super nice because they work without extra dependencies. And here I'm using the $sign that Simon doesn't like too much, but I always use the entire name, so it always works for me. So base R plots, it's super versatile. It can make lots of different plots, and it's has like default function. So like you can call plot on a mermod object, like Simon mentioned, which is an object that comes out of a linear mixed model. And it will give you like a default descriptive plot of your model. It's super nice. It's super quick, and there's no like extra library calls to get it in. It's very, yeah. But it's not necessarily like the prettiest thing. Then again, like our papers don't necessarily have the prettiest plots, but usually you'd want to do a bit more with it, and it's not always the easiest. One of the reasons I don't like base R plots is because it's not stored as an object in R. It's one of those things that doesn't get stored as an object. So you can't continue working on it. Like you can't assign a plot into an object. That's not going to save anything. So that kind of messes with my head with like the normal base or the normal way R would usually work. But ggplot2 does save to an object. So so that kind of works with my mentality. So the next couple of slides I'm going to go through, I'm going to go pretty fast. Don't fret, because I will soon switch to live coding and I will build the same plot together with you slowly so you can follow a bit more easily, and I can talk kind of out loud as we do that. So I just want to go through the next slide so you can kind of see the progression of building a ggplot. So here I've made a data frame called DFLong, which we'll be using throughout at least my talk and Delia's talk, and also Rick's at the end. It doesn't work so well for structural equation models, so I don't think Roger is using it. But the script to simulate the data, DFLong, is in the OSF portal, so you can grab it from there. So here first, I'm just starting with calling ggplot and saying data equals DFLong. And it literally creates this gray square on the side of my slide. And there's nothing there but a gray square, which is not particularly interesting. But there's a ggplot actually doing something. It is preparing the graphical representation of a plot. It just doesn't know what to do yet. It's just got data, so it makes a square and has no idea what to do. We continue on and telling inside ggplot, here we come with the mapping. In DFLong, there is a column called age category and another column called FFA. And the age category is a categorical variable of age. So if the participant is a child or an adolescent. And in the FFA column, we have a numerical vector of fusiform face area activation. And you can see now ggplot has actually done a bit more with the square. So it now has axis information. So on the x-axis, where we said we wanted age category, it now has age category as an x-axis and child and as adolescent in two different places. And then on the y-axis, because it's a numerical value, it goes from -10 to a bit over 20. And the reason it goes from -10 to like 25, 30-ish is because it sees into DFLong and it sees the values of the minimum and the maximal values of the FFA column, and it scales the plot to that. So it's already prepared like a grid for us to put something in. But we've not put anything in. Like we haven't told ggplot what type of plot do we want yet. So we do this by adding a geom. And here I've added a geom box plot, which gives us standard box plot information. So this should look more or less exactly like the base R plot. We have the quantiles, we have the median inside of the 50% box, and then we have small dots that are like the outliers from the distribution. So here we get like a very clear idea of what our data looks like. And we can continue doing fun things. Like here, I've used this AAS function again, which adds the mapping. I didn't actually explicitly say mapping in front of this AAS. ggplot is very smart. You can put the AAS wherever you want, and it will know that it's mapping. So here I said, fill the box plot based on the age category. So now the child and adolescents, even though they have each of their x-axis positions, now they also have colors so that we can more clearly see the difference between the two groups. And I've used fill because the box in the middle is a rectangle, and that takes fill to color it. And I can change the color by adding a scale fill here with like a brewer palette called Dark 2, which is a fair enough color. I can change the theme. As you can see the difference here, like we have the gray background. It's a little bit boring. Most journals won't actually accept that. So we change that into the theme light. So just adding a theme light, and then it's whiter. It's a little bit cleaner to look at. And here I can start adding lots of labels, and you can't actually see all of the text because it's a bit much. It goes and goes. But you can see like I've added a table to the top. There's a subtitle right below the title. The X and Y axis names have now changed to a little bit nicer than just like the default column names, which weren't very nice. And then for the fill, which is an aesthetic that I've added, I've also said that the legend name for that should be each category. So it's like a nicer thing for publications. And then we can add even more types of geoms to the same plot. So here I've added geom violin after the box plot. But this is not particularly satisfying because the violin actually is placed in front of the box plot. So now we can't see the box plot anymore. So that's kind of ruining my idea. But we can change this by just switching the geom violin to come before the box plot. So ggplot actually adds each of these geoms in the sequence you give them. So you can kind of customize it by making sure that things come in the right sequence. And because I've used fill like both in the violin and the box plot, I can do a little bit more customization by moving the fill up to the ggplot call, which will give the fill to both of the geoms that I've used. And then I've set the opacity, the alpha, the transparency of both violin and box plot to 0.5. So they're semi-transparent. And notice that here I'm setting. So before I was mapping, but now because alpha, I'm not varying alpha, I can't put that in the ggplot call. It's not gonna propagate into the rest of my geoms. I'm setting alpha to a single value, and then I need to put them in both of my geoms. And I've also set the box plot to be slightly narrower, so it doesn't kind of overplot with the violin. So now I have both a nice density plot of the data, and I have a nice box plot telling me how the distribution actually looks with the percentiles and the median. It gives me a super nice idea of what the data actually looks like. And again, we can add even more to this. So let's add the dots. This looks horrid, like it gives us no information. It's just like a band of lots of dots. Let's not do that. So there's actually a pretty nice geom for adding dots to a density, which actually I picked up from Delia's plots because I don't actually use it that much. And it's called a dot plot. It takes a little bit more of tweaking to get a dot plot to work as you want. Like in this case, I need to tell it that the axis it should bin along is Y. I need to tell it to stack along the center. I need to tell it the dot sizes in this case because there's a lot of dots. It will just completely fill the screen if I didn't reduce them. Again, I set the transparency of the dots a little bit because there's so many. It didn't really matter because there's still so many, so they're completely overplotting. And I needed to set the bin width to 0.045 to actually contain them within the violin I had. And this was more like trial and error for me to figure out how to make it work. And that's kind of how a lot of ggplot stuff works. You kind of trial and error until you figure it out. And the last little bit I want to show is a facet. So sometimes we want to create subplots of like the same structure, but we want two different panels, which I could do here. Like there's a third column in this DF long data frame that's called face emotion that tells us about the stimuli that has been presented to the participants of this experiment. And here I could plot the distributions for these two different stimuli for both of my groups next to each other. And I'm applying the exact same function, like the data looks exactly the same. So it's not, in this case, it's not showing me particularly much, but I am able to plot them. And it's just a single extra line of code. So I have like 4 minutes to do some live coding. So here I have, I've placed the scripts that simulates the data in a particular place on my computer. So I'm just sourcing it so I can call the simulate data function. And now in my environment, which is in a slightly different place than where Simon had it, this is my environment down here. I have now dflog, which has like tons and tons of observation. And I'm going to call library ggplot2. I'm not supposed to have, I mean, it works, but it's not nice to have that extra space there. Calling ggplot2 so I can start preparing my data. So my plot. So we're going to go ggplot and data equals dflong. And I like having some space between. And then mapping equals AS. So on the x-axis, we're going to have, actually, let's have a look at dflong before we continue, because it's a good idea. So dflong is a tibble, which is a type of data frame. You don't have to think about that. We have an age category column. And then we also have, like later here, we can see we have an FFA column and face emission, which are the ones we're going to be using here. So we're going to, again, put the age.category on the x-axis, and on the y-axis, we're going to put the FFA. And then you add a geom or a scale or a chord or whatever with a plus sign. So this is very specific to ggplot. You add extra kind of elements with a plus sign. So we're going to add a geom box plot, and we're just going to leave it at that for now. And I'm going to execute it with command enter or control enter, and then it pops up down here in my plots viewer. And this is what we started with before. So I'm going to add fill equals age category, which is another mapping of aesthetics to the fill. There we go. Now the squares are filled. Let's put in the Geom violin as well, because it is, I do really, really love a good violin plot. But now they're overplotting each other, and that doesn't look nice. So we're going to reduce the width of the box plot to 0.2, which is going to take 0.2 of the width that it has. That's much nicer now. They're contained. You're kind of retaining all of the information, but like the color is a bit garish, I think. So let's reduce the alpha to 0.5, which is semi-transparent, which is something I use quite a lot. And then it becomes a little bit more pleasing, in my opinion. You could do this by just the colors, but when they're semi-transparent, it also means like you can see the grid structure in the background. So it's easier for people to see exactly like where the distribution has its different like widths and the narrowness of it, and you can also add different things behind it. And I'm going to skip the dot plot for now, because it takes too much time. And then we're just gonna scale fill brewer with another palette, which is dark 2. And this is kind of, you just keep on going and adding, and you just if you don't know what kind of geom you want, usually I'll just type geom and I will let RStudio suggest for me what I can choose, and I kind of play around until I find the geom I want to use. So I think that is more or less my time, which is up. But just to show you, like very briefly, other things you can do with ggplot. I made a package that creates brain atlases with spatial data. And this works just like any other ggplot kind of syntax, and it's super versatile. And really, like, ggplot is great for creating extremely custom plots. And here, even combining a bar chart with like this spatial object type of plot. So it really is extremely versatile. It does take a lot of time to kind of start navigating, but once you do kind of crack the code, I think it's a very cool tool. So that is my time up, I believe.
Brilliant. Thanks, Mo. That was absolutely fantastic. So we'll wait a few moments for any questions to arrive. I know that one question arrived for Simon's talk.
Cool.
Hopefully Simon's still with us.
Yes, yep.
So do you want to read aloud the question and answer it, please?
Yes, so it was a very good question, and I skipped over this. The question was, how do you know what the arguments to a function are? And so the way you access that information is, one, you Google it, or two, if you're in R, there's a help function, and that brings up the help file for a function. And the anatomy of a help file is very important. So the first bit is a description that tells you what the function does, always useful. The second bit talks about how you use the function, and the third bit lists the arguments. So it's a section in the help file called arguments, and it gives you the names of the arguments and then a short description of what they are. And the next most important part of a help file is you scroll all the way down to the bottom, and there's an example section. So the bottom of every help file in R has an example section that shows you examples of how to use the function, and sometimes has little comments that tell you what they're doing. So yeah, it's a very important. Also, just as another nod to using RStudio, you may have noticed while live coding was going on, you saw the little boxes pop up in RStudio that gave you suggestions for the arguments. So RStudio gives you the argument names as suggestions, which is very helpful. And obviously, I'll wag my finger at the use of $$ notation.
Okay, Mo, there are a couple of questions for you. I don't know whether you've seen them, if you want to read them out. I think you're still muted.
Yeah, I turned my microphone out. So I can see there's a question about wrangling your data into like the correct format for ggplot. That is like I literally do 2-day courses in wrangling data. It is a bit tricky. I absolutely super recommend there are for data science online book that you can find. Like, it's free online. You can also buy it on Amazon if you want to support the guys writing it. It really does take you step by step through your data wrangling needs, i.e. kind of squishing the data into the correct shape or changing the names of variables in a very specific way called like the tidyverse way, which is super powerful. Not everyone likes it, but it works brilliantly with ggplot too. So if you're going kind of for that type of aesthetic, learning the tidyverse, other types of functions might be a good idea because they do work together so well. So that's especially important for the facets. And I have an extra question about the facets I can see. So a question is, I'm not sure I understood. Is the facet wrap function basically just an identical plot next to the already existing one, and then you customize it? No, actually, I wasn't able to create facets for this data set that very clearly shows what the facet does. They are not identical. They contain the exact same components, but based on the data in the column that you facet by, it will change the plot. I do have a suggestion for something I can show you that should show the facets a little bit better. So I'm just sharing my screen. So instead of going by facet identity. I tried another plot that didn't work. I'm going to facet by age category again. So now instead, I'm still going to have actually adolescent and child on the x-axis, but I'm also going to facet by it. So it should give us this. It's not particularly satisfying plot, but it kind of makes my point. The facets are not identical. They plot the different things you ask it to. It's just that the data example I was using wasn't showing that. So now this facet only contains the child data, and this facet only contains the adolescent data. So they're not the same, but it's a way of kind of showing that there might be different distributions, there might be different kind of properties in your columns, in your data based on other categorical variables in your data. So it's a way of kind of exploring that or even showcasing that in a paper. Yes, and then there's a last question. Do I have time for that? Yeah? Okay. Yeah. So there's another question. Actually, there are several. So I'm wondering how one can see what option is available for styling, e.g. what is available for Geom violin. Now, Simon already pointed out how the help functions work. So we're going to do a help Geom violin. And as he said, the help function, like the anatomy of a help function is absolutely, it takes a while. It does take a while to get used to. And the geoms are kind of even more tricky. At the top here, you can see these are default options for Geom violin. This is what Geom violin does without you doing anything. It draws the contour, it trims, it does some scaling, it doesn't remove NAs and stuff like that. And then we can kind of scroll down to the arguments and it describes all this. But the key part actually of a ggplot help file is this part. You scroll down to the aesthetics. And the aesthetics tell you what parts of the geom you can control. In this case, in bold, I don't know if you can see that they're bold, but X and Y here are bold because a violin needs to have an X and a Y. If it doesn't get an X and a Y, it doesn't know what to do. So you need to tell it X and Y. And then you can set the alpha, the color, the fill. So the color would be the edge around the violin. The fill is the inside of the violin. There's a grouping function. There's a line type. If you're very particular, you can make it to dashed or double line or whatever. There's a size and there's a weight. And then there are also computed densities. So the geoms, depending on the geom, their help files are actually quite intense. So I would recommend looking at them and then kind of playing around until you find something that you like. Or if you're after something extremely specific, literally Google that exact thing you're after. ggplot2, how do I make a dashed contour? And you'll probably like get an answer for it. Yeah.
Okay, thanks, Mo. I'm so glad I'm attending this course because I'm learning so much as we go along. But thanks again. Our next speaker is Delia Furman, who's at King's College London, and she'll talk about univariate stats. Over to you.
Thanks, Rick, and thanks to the previous speakers. That was really super useful. Okay, I am going to share my screen. Okay. Ooh, now I'm getting a fun visual effect here. Sorry, I'm just trying to pull up my art. Okay, brilliant. Right, so I'm going to start straight away working in RStudio. As you can see, my layout is slightly different from the previous speakers. So I've got my script up here. You can see my environment here. Plots will come up down here, and this is my console. All right, so I am going to talk about univariate statistics and R. So this is all sorts of tests that we can run with just a single outcome variable or dependent variable. And we're going to take a frequentist approach in this section, while Rick in one of the later sections is going to take you through Bayesian approaches. All right, so before we get started, we need a few packages. We're going to need ggplot, which you're now very familiar with. We're going to need car, which has some stats functions. LME4, which Simon mentioned as well, which contains a lot of useful functions for linear mixed models. And I will need dplyr for some data wrangling, so we're going to do some data shaping as well. Okay, I am going to load the datasets I will work with today. You already know dflong because Mo showed it to you. I am going to also load a dataset called df_avg or average, which contains just some average data from dflong. So the first thing I thought we'd do is run a paired t-test just to kind of ease into it, because I think everybody will be familiar with a paired t-test and we'll run it before either in SPSS or in MATLAB. What we're going to do here is we're going to look at df average. I'm just getting the first few rows using the head function here. You can see that we have the participant number, we've got the H category, and we've got FFA, which stands for this fusiform phase area activation. You can see that we've got 2 rows per participant. So once when they were a child and once when they're an adolescent. So this is some repeated measures data here. Participants are measured at least twice. I'm going to plot my data. So this is now a much less pretty version of the plot that Mo showed you already. I had major plot envy there. But basically, you can see the data when participants were children here, and then here when they're adolescents. And in red, you can see the individual data points, and the lines show you the changes of participants over time. Now, it looks like children have slightly lower FFA activation than adolescents. To see whether this is statistically significant, we can run a paired t-test, of course. Now, in R, we can do this using the t.test function. As the previous speakers mentioned, if we're ever confused as to what we need to tell R, we can get help by typing help down here, or as I do it, typing it up here in the search function. So if I get t.test, then I'm going to get lots of useful information and my examples at the bottom, which I think is always a nice place to start. Okay, now with the t-test function, we need to start by telling R our model formula. So the model formula is going to contain the dependent variable and the independent variable. In our case, the dependent variable is FFA, fusiform phase area activation, and our independent variable is age.category, so whether participants were children or adolescents. Now, it's important to note here that the names of our dependent variables and independent variables need to match our column headers. Otherwise, R isn't going to know what variable to analyze. And yeah, also important to say that we need to keep this order. So we need to start with my dependent variable, then we have to add the tilde sign here, and then we have to add the independent variable. So we can't switch this around. Then we need to tell R that we want to run a paired t-test using paired equals true. And then we are going to tell R which data set to look at. So we here have data equals df avg. I'm going to run this, and I'm going to get my results down here in the console. So you can see that we ran a paired t-test, and we're getting our t statistic here, so that's minus 13.82, degrees of freedom of 49, and this is my p-value, which in this case is really low, so this is going to be p smaller than 0.001. I'm getting a confidence interval here, and I'm going to get the estimated mean difference. So this tells me that on average, participants' FFA activation was about 9 units lower when they were children compared to adolescents. Okay, great. So now we've run our first test here. The next thing I want to do with you is to run a repeated measures general linear model, or GLM. So I think lots of neuroscientists use GLMs quite a lot. Now, for the GLM, we're not going to work with the average data set because, happily for us, regression models are really happy to work with trial level data, and that's always a good idea if we can. So I'm just going to pull out a couple of the columns of df long here. So we're going to, again, look at the participant. We're going to have participant's age in there. So this now is not a category anymore, but it's continuous age measure. So this will be 10 years here. And this variable was actually used in order to then create the categories of children and adolescents. We've got another variable here called face.emotion, which is the experimental condition that Mo mentioned. So this is happy versus sad faces. Which type of face did participants look at? And here we've got their FFA activation. Now you can see that we've got lots and lots of rows for just a single participant, and this is what we call the long format. Okay, so now we're going to set up our repeated measures GLM. To run the repeated measures GLM, I'm going to use the LMER formula, which comes from the LME4 package. So if we type this in here, we can see that what we're actually doing is we're going to fit a linear mixed effects model. The reason for why we can use this function is that a repeated measures GLM can be conceptualized as a special case of a linear mixed effects model. We're going to talk more about linear mixed effects models in the next section because I think they are super useful. Okay, so we're going to start again with our model formula. This actually looks really similar to what we did for the t-test. So we've got our dependent variable here, FFA, we've got the tilde sign, and then we have our independent variables here. So we now want to look at both participants' age and the experimental condition called face.emotion. And we want to look at their interaction effect as well. And we do that with this little star sign here. So in all sorts of linear models in R, the star sign allows us to request both the main effects of two variables and their interaction. If I had typed just a plus here, I would just get the main effects. If I typed just this, I would just get the interaction, no main effects. And by adding the star sign, I get everything, which is nice. All right, and then we need to add something that tells us that we're dealing with a repeated measures data set here. And this is what this line here does. So this is a very specific syntax. We're going to talk more about the syntax in a second. For now, just note that this allows us to account for repeated measures. In this bit here, you will need to name your participant column. So in my case, this is called participant. In yours, it might be called ID or whatever. But this is where you would put that variable name in. And then we want to look at df long in this case to get the trial level data. I will run this, and you can see that I don't immediately get any output here. This is because I've sent my model into a new model object, which I really creatively called M1. I did this so that I can now run some nice stats on it. The first thing I'm going to do is I'm going to get a summary of M1. The summary function is really useful in R. So if you're running any type of statistical test and you're not sure how to get the output you like, try the summary function first. It really works with a lot of models. Okay, so I'm getting now my output down here. So it starts up here where R just kind of regurgitates a little bit of the information I gave it. Then it goes on to some of the statistical things it does in the background. And then it gives me the fixed effects estimates, which is what I'm primarily interested in here. So as with any regression model, I get an estimate for the intercept. And then in this case, I get three slopes. So I get the slope for participant age, for the experimental condition, face.emotion, and for the interaction effect. And you can see that I get estimates, I get standard errors, and I get the t-value here. Now you'll notice that p-values are conspicuously missing from this output. The reason for that is that I believe that the developers of LME4 don't like p-values, but naturally people found a way around this and gotten p-values anyway. And one of the ways to do this is with the ANOVA function from the CAR package. So if I run this, then I am going to get chi-square statistics, but that's completely fine. They're the degrees of freedom and their p-values. What you can see here is that we've got a significant effect of age. So there's a relationship between age and FFA activation. No significant effect of face emotion, and no significant interaction effect. So if I want to see now what's actually happening here in the relationship between age and FFA activation, it might be a good idea to plot it. And in this case, I'm going to plot the model predicted values using the predict function. Now, because this data set is so huge and I don't want to plot every single data point in there, I'm going to summarize my data a little bit. So this is some data wrangling. And then I will plot it. You can see here that we've got this kind of nice linear relationship between participants' age and participants' FFA activation. So the older participants get, the higher their FFA activation. Now, I mentioned that this type of repeated measures GOM is actually a linear mixed effects model. And the specific type of linear mixed effects model that this is a random intercept model. Now, why is it called a random intercept model? I can show you if I plot each participant in a different color. So you can see here that I've got quite a busy plot with lots of different colors. Each of these colors represents one participant. And you can see that what I actually did under the hood was basically get an individual regression line for each participant. So each participant here is allowed to have their own intercept or baseline FFA level. You can see that all the lines are parallel, which means that the slope is exactly the same for each participant. So the slope is fixed. But we do have these random intercepts here, and this is why this is called a random intercept model. Now, we're going to build on this model and include a couple of other interesting random effects. But before I do that, I just want to briefly give you a little bit of background about mixed models in case you've not worked with those before. So linear mixed models are called mixed because they contain a mix of fixed and random effects. You will be really used to fixed effects. Fixed effects are variables whose levels are fixed or not random. So you can think of things like experimental conditions. So in my case, my experimental conditions were happy versus sad. I didn't design any other conditions. Therefore, these levels are fixed to just 2. Other common examples are things like experimental groups, often other variables of interest. Now, random effects, in contrast to this, are variables whose levels are sampled from a larger population of levels. So the most classic random effect is participants, right? If I run my fMRI study, I'm not going to be able to scan all the humans out there. Instead, I have to sample a few and look just how excited they are to be taking part in my experiment. Now, there are lots of other random effects that are really interesting and might be worth accounting for. So if you're, in educational research, you might have random effects like participants' school or their class. If you're in more sort of, medical research, you might have things like participants' healthcare provider, their hospital, or other variables like this. And if you're an experimentalist, you probably have a random effect called stimulus. So if we run an experiment, we normally can't show people all the possible stimuli out there. We have to sample a few, right? And accounting for this is probably a good idea because all of these types of random effects create dependence or correlations in our data, and it's often a good idea to account for that. And we can start to actually look at these types of variables if we're interested in them, which is another nice thing to do. Okay, I'm going to head back to my script. So I said we will build on the model we just ran now, and we're going to include another random effect here. In this case, the random effect is going to account for the stimulus. So if I get a few more columns out of my df long, and see that we still have participant age, face emotion, and FFA activation, but we also have face identity here. So you can imagine that these first 5 rows here, for instance, show my face, and then, the next row here, row 2, maybe shows Roger's face or whatever, right? So these are my stimuli that are accounted for here. I am now going to run or set up a new model called M2. The beginning of this model is exactly as you would expect from the model previously. So we've got the LMER function. We're setting up our model formula. We've got the dependent variable, and we've got the independent variables here. And now down here, we're getting our random effects. So these here are our fixed effects. Down here in brackets, we've got our random effects. So let's start with this line here. So here we're now requesting a random effect for face identity. Okay, so this is to account for the stimulus. And what I'm doing here is I'm asking for just a random intercept. And the random intercept is requested through this 1 here. So I've got a 1, then the down slash, and then this face dot identity. So this tells me that I want a random intercept for each face identity. Now up here, I am requesting a random intercept for each participant. I want, again, to have a random intercept. I do that by having this 1 here. And then I'm going to add another random effect here. And what I want to do here is to ask for random slopes. So I want to allow participants to show different changes with age. Okay? And I do that by repeating the name of the fixed effect for which I want to allow random slopes here. So I've got the 1 here to ask for a random intercept, and I've got the name of this of the variable for which I want slopes here. And then this is the random effect that I'm asking for. Okay, so I will run this, which takes just a couple of seconds. And then I'm going to get my model summary again. Now we can look at the output in a little bit more detail. So again, at the top, I'm just getting what model I asked for. And then here, I am getting some information about my random effects. So you can see, for instance, that we asked for a random intercept for participant. This tells me that we asked for a random slope. And this tells me that I also asked for a random intercept for face identity. And you can see the estimated variance and standard deviations here. Now I'm getting my fixed effects down here, and they're exactly as they were before in terms of its output, right? So we still have the intercepts and the slopes. If I run my ANOVA over this, then I can see that I still have a significant effect of age, and nothing else here is significant in terms of face emotion or the interaction term. Now I said that we were estimating a random intercept and slope model here. And I'm going to show you this in my little plot here. So it's, again, quite busy. But what you can see here is in different colors, different participants. And you can see that we've allowed individual intercepts. So the starting point is different. But we've also allowed participants to have different slopes, right? So the changes over age are different. And this is really nice and naturalistic. Often, you know, random slopes models are quite naturalistic in terms of we would expect participants to also show these differences. All right, so this is it from my section. I'm now going to head back to the main screen.
So again, please type any questions you have into the box. There aren't any at the moment, just lots of private discussion between the speakers about different statistical approaches. So ignore those, Delia. We haven't got any questions yet from the audience, but they might come in the next talk. So if you could stay online, maybe there'll be some questions for you after Rohir's talk. So thank you again, Delia. That was really clear and really important stuff. So Rohir, are you ready to take over?
I am.
Brilliant.
So just let me share my screen, the whole lot. So I think you should now see my PowerPoint. So thank you very much for hanging in there. I assume you're still hanging in there. I can't know for sure. The next half hour, 25 minutes, I'm going to be talking about using R for multivariate statistics, building a little bit on the introduction my colleagues have given me before now. So just to give you a bit of a walkthrough, I'll talk about an overarching analytical framework called structural equation modeling, which can do most of the things you might want to do. I'll introduce a package I recommend you use. I'll show you how and why to load, check, and manipulate data. And then we'll first start with some very simple models using Levan, which is the package I'll be introducing shortly. then some multivariate and multivariable models, and then finally I'll show you some superpowers in lavaan, as well as how to fit confirmatory factor models and full SEMs. So what is SEM? It's a class of technique. It has its roots back to the 1920s by Schuyler Wright, who wanted to estimate the causal effect from guinea pigs onto their descendants and drew this lovely figure. And it's a combination of two tools of path analysis, where you simultaneously estimate multiple regressions, and latent variable analysis, where you relate measured variables to hypothesized constructs. There are many excellent introduction books that I won't kind of go through in detail today, but there are lots of resources available online. So the tool I recommend is lavaan, which is short for latent variable analysis. It's developed by Professor Yves Rossel. I know for a fact that they get very little institutional credits for working with these types of packages, so I wanted to make sure I flag up the work he's done on making this very accessible open source package. You can just Google lavaan tutorial, and it'll basically take you step by step through the things you might want to do, and I'll show you some of what I think are highlights and basics. So today I'm going to be working with an example dataset, which is included in lavaan. So first you install a package, which is in the code that I shared, and then you load it in like this. And we're going to use the Holtzinger-Schweinfurt dataset. So that's a dataset that has a number of demographics and a set of 9 cognitive tests. So these cognitive tests are called X1 through X9. There are various kind of types of puzzles and challenges that a group of 301 children did. And we're going to figure out the relationship among these variables and perhaps how they interact with variables such as gender or age or school. Now, the first things I think you should always do, and everyone learns this the hard way, is first use the function head that others showed before me to just give you a sense, is the data frame the way you think it might be? Then do some univariate plotting just to see whether your data makes sense, and then some bivariate plotting. And let me just get you started. So here, hopefully you'll see my screen now. I'm going to load the lavaan package like this. And we load the data set Holtzinger-Schweinfurt. First we run head. So does this look like we want it to look? And so far it does. So it has ID, sex, age, year, month, etc., and the 9 cognitive variables. So far so good. The first thing I recommend you do is to also plot the data. And there's a lovely package called summary tools, which you can load. And then you can do this function, which is I want to view a summary of my data frame, and I want you to show me columns 2 through 15. So presto. So this takes you through all the columns you asked for. So that's sex here. It shows you a number of things you probably care about, including the minimum, mean, and max. It shows you the frequencies. It shows you the percentage missingness, and gives you this nice histogram. So Simon mentioned at the start that sometimes people use 999 or minus 999 as a value code for missingness. Now, this is exactly the moment you would find out that, say, 999 is being coded as an actual value. So you might have a bunch of kids who have these scores, and there's some way off here over on the right coded as 999. And that's the moment you realize that you don't want to analyze that in your data. So this is a very useful function, and I highly recommend you always run it before you proceed any further. Now, secondly, we're going to be looking at relationships among these variables. So we don't just want to look at the univariate plots, but we also want to look at the bivariate plots. And this is other package called ggAlly, which builds on the ggplot package that Mo introduced. And we're going to load it. And it does this lovely thing, has this nice function called ggpairs, where you can say for a set of variables, and I can recommend not using too many here, we're only going to plot the 9 cognitive tasks, X1 through X9. And we're going to show basically what those relationships look like as follows. It often takes a few seconds to just plot it, but I promise you it's worth it. So immediately we can see variable x1, 2, 3, 4, 5, 6, 7, 8, 9, and we can see the pairwise relationships between any pair of relationships here. So again, we get the histogram on the diagonal. That all looks fine. We see the correlation with significant stars if you're interested, and basically everything looks kind of like the way we want it to look. And before we get started with the functions, there's one more thing to note, and this is the type of thing you will encounter in your own data. Remember, when we looked at the head of the data, we had these 2 columns, age in years and age in months. Now, nobody knows why that happened, but of course, that's generally not the way you want to analyze it. So the first step, we're going to just compute a new variable called age full, where we add the age in years and the age in months divided by 12, just to make sure we have kind of age with a proper final resolution. And now we can just rerun the same command before, head, and we now have age full, which makes far more sense. And now we have kids in kind of not just age in years or in months. So now we can go get started. So let's get back to the basic syntax in Lavaan. So these are essentially the 4 operators you might need to use in Lavaan. So firstly, there's the equals and then tilde operator, which is measured by. And we'll only need that when we get to latent variables right at the end. The second, probably most common operator is the tilde, which Delia also showed extensively, which is a is regressed on command. Third, there's the double tilde, which are used for variances or covariance or residual variances. And finally, and that's one we won't spend time on today, which is the intercept of the mean, where you have tilde and then 1. One of the nice things of SCM is that it's kind of a Swiss Army knife. So all of the techniques you might have used in the past, including t-tests and correlations and regressions, etc., are all essentially simple versions of SCM, which means that if I can show you some of the basic syntax, you can essentially run all these models within the same framework, which has some nice properties, I think. So how to run a linear regression in Lavaan. So I'll walk you through the syntax here. So firstly, we have the name of the model, in this case, the very creative regression model. And then we have the command or the model syntax. So in this case, we're going to regress x8, which is one of our cognitive tasks, in this case, the speeded dot task, and regress it on age full. So we're interested in the effect of age, and we think that older kids are likely to do a little bit better on this particular cognitive task. And then the function, as Simon explained, is SEM. So that's a very general function that will fit essentially any SEM model you throw at it. Here's the name of the data frame, and Lavaan is smart. So as long as these names here are column names in the Holzer and Schweinfurt data set, then it'll find them and it'll use them. And here's the name of the model output. Sorry, Delia, I highly recommend using informative names. So in this case, fit regression model rather than model 1. I say that as a person who has named many things model 1 and regretted them after a while. And things we won't spend too much time on today are you can ask for fit measures for SEM and you can ask for standardized effects. So this we'll use. So this will give us a kind of a column output that has standardized effects. So instead of raw betas, you'll have standardized betas. So it's a bit easier to kind of just at a glance look at the effect sizes in the model. Now, with this basic syntax, we can build it up to more complicated models. So we can have a multivariable regression where we have one outcome, this speeded cognitive task, and now have multiple predictors. So here we have age full and another cognitive task. So here we're interested, can we predict how well you do on one task by your age, as well as how well you did on a different task? One thing you can now easily do in Lavaan that is not so easy in standard linear modeling tools is multivariate regression, where we have multiple outcomes. So we might have x8 and x7. So 2 different cognitive tasks predicted by both age and x9. And finally, we can fit a mediation model where the same variable, in this case x9, can both predict things. So here x9 is predicting x8 and predicted by things. So in this case, x9 is being predicted by age, but is itself then playing a causal role in predicting x8. That's the kind of thing you simply can't do in functions like LM unless you really kind of hack the function yourself. So let's have a look at those, how those work in practice. So here we have our simple regression model. So we're going to run this and we're going to ask for a summary of all the things we want to know. So here we have the effect of age on x8, and the final column, I'll just drag it a little bit so you can read it more easily. The final column here is the standardized effect. So you can see age has a strong and significant effect on x8. And if you want to verify that a linear model is just a simple SEM, we can rerun it as a LM, which is the general linear model function in R. And we see, again, 0.2463. So we get exactly the same result. Now with the multivariable model, same principle, an outcome, 2 predictors. Run it like this. And now we have the effect of age is 0.2, and above and beyond that, the effect of x9 is very sizable 0.42. And then finally, the types of things you can't do in a simple modeling framework is have multiple predictors and multiple outcomes. So here we're predicting both x8 and x7 in the same model. So x8 is predicted by age and x9 with these effect sizes, and x7 is also predicted by age and x9. But here you can see age does not seem to have an effect on x7, at least not above and beyond the effects of x9. And then finally, mediation. So some of you might have used a mediation model before. So the unique thing here is that one variable can both be predicted by something and itself predict other things. And in Lavaan, this will split out your mediation effect here. So the mediation effect is A times B, which in this case is not significant. Right, now I promised you some superpowers. There are two in SEM. First are model comparisons, and second are parameter constraints. So model comparisons. So one thing I hope you take away from today is to think about everything as a model. And there's a lovely paper from about 10 years ago on a quiet methodological revolution where we changed from just estimating parameters to testing and comparing models. So there are two ways to go about model comparisons, and I'll give you examples of both. So one is we specify one model and we see how well it does. In other words, is it a good or a bad model? Now, this only works if your model has degrees of freedom. In other words, we need to remove our training wheels, and we need to have a model that's simpler than the data we gave it. The second way is that I think is probably the most useful way for you to get started is we have two models that differ in complexity. And the question we ask is, does the more complex model significantly outperform the simple model over and above the expected improvement given more parameters? In other words, a slightly more complex model will always do slightly better, but we can penalize the added complexity and then say, well, on balance, which of these two models is to be preferred? So how? And the second superpower is parameter constraints. So the nice thing in Lavaan is we can fix any parameter to have a certain value, such as 0, if we say our hypothesis is that this does not have an effect. It can be equal to another parameter, and I'll show you why that might be interesting. Or it can have other constraints. So you might test a model where you say the effect of h must be at least 0.5. The nice thing is from this perspective, scientific claims become model comparisons. So in Lavaan, you fix a parameter by preceding it with a numerical value or giving it a label or a name. And if you give two parameters the same label, then they must have the same value. So how do we do model comparison? Let's think about the regression model where we had age predicting some outcome. So instead of fitting one regression and looking at the p-value of the parameters, we might instead shift to a way of thinking about two competing models about reality. The first is model A, age affects speed dot counting. And the second is model B, which is a representation of the world where I say age does not affect speed dot counting. To test this in Lavaan, and model A is simply the same we had before. X8 is being predicted by age full. And model B is X8 is predicted by age full, but I fixed the regression coefficient to 0. In other words, I test the same model, but now testing it under the assumption that the effect of age is 0. How do you compare models? Well, there are two ways. So one is the likelihood ratio test, which is essentially the question, does the more complex model significantly outperform the simpler model over and above the expected improvement given more parameters? So a more complex model will always do slightly better, and the likelihood ratio test gives you a significance value of whether it does better than expected just by being a slightly more complicated model. So in this case, the model where we constrain age to 0 does very poorly, and the model where we estimate it freely does significantly better. In other words, we need to freely estimate age to have a proper representation of the data. So this significance basically means the model where you freely estimate the effect of age does significantly better than the one where we set it to 0. However, there's a drawback of this likelihood ratio test is that if this comparison is non-significant, then we really can't make many claims either way. And there's other technique you can use. So you can look at the AIC and the BIC, these information criteria. So these are properties of the model that balance how well they explain the data and how complicated they are. So if you look at these columns, AIC and BIC, then lower is better. And we can use this trick that Wagemakers and Farrell proposed, and we can transform these AIC and BIC differences into Aka-Ika weights, which gives us a way to quantify how much more likely is model A versus model B given the data. And the nice thing is this is symmetric, so you can also have evidence in favor of the null, and Rick in the next talk will go into a bit more detail there. So in this case, there is an overwhelming preference of the model where age does affect X8, compared to the model where we hypothesize that age does not have an effect. How about equality constraints? So say we have two models, one where we say our hypothesis is that age has a different effect on letter reading than on dot counting. So now we have two outcomes. We have X9, which is letter reading, and X8, which is dot counting. And we add two labels here. So we give a name to the regression coefficient, reg1 and reg2. And because we give them different label names, you can see here on the right, that the coefficients are allowed to differ. They're just given a name. However, say someone else has the hypothesis that age has the same effect on letter reading as on dot counting. So whatever the effect of age is, it must be equal to both. So now instead of having reg1 and reg2, we now have just reg and reg, which Lavaan interprets as I want these parameters to be identical. So it forces them to be identical. In this case, it's the standardized effect is 0.18, which is about halfway between these two effects. So the final step we can take, and then I'll show you what it looks like in Lavaan, is a multi-group model. So what is a multi-group model? Well, that means we add one command, which is group equals group name. So you can ignore this part for now. And here you can see group equals sex. So in this case, we're going to just fit the same exact model, where we predict X7 in this case by age full, and we can fit it for two groups. And it'll basically estimate the same model for each group independently. However, we can now use this trick of equality constraints across groups. So if we look at the labels here, we here have a vector, which basically means it's going to give labels to the value for the boys and for the girls. In this case, the parameters are estimated equally. So we're testing the hypothesis that, they're not made equal, they're different. So here the effect of age on X7 is different for boys and girls. And here we give it the same label, so it's forced to be equal. In this case, the effect is non-significant. In other words, the more complicated model where the age effect is different for boys and girls does not significantly outperform the other one. But we might want to translate that into evidence in favor of the null, which we can do here, looking at the BIC weights. So in this case, the model that says the gender effect does not differ is about 15 times more likely given the data. And Rick will go into this kind of way of thinking in a bit more detail later. Right, for the final step, we'll go through latent variable analysis. So often we might care about a hypothesized construct, such as what is your memory capacity. So latent variables are ways to formalize the relationship between the latent construct and observed scores. So it helps you reduce your measurement error, and it helps you understand your data, increase power, and simplify analyses. Just to give you an example of what I mean by reducing measurement error. So this is real data from our CamCam dataset in Cambridge, where we have the sum scores on a set of cognitive tasks at time 1 and time 2. That's about 5 years apart. So if we just take the sum scores, then they're pretty highly correlated, but they're a bit noisy. But once we estimate latent variables, so we try to remove some of this measurement error, then this is what our data look like. So this is very much worth your time, in my view. So there's some benefits of using latent variables over observed scores. They offer a more parsimonious model. So instead of having age-related changes in 11 tasks, you might have age-related changes in 2 constructs, working memory and processing speed. It improves power. So it might give you a bit more precision, decrease your sample size. It gives us a principled manner to refine constructs. So we might say, well, these 11 tasks all measure working memory, or you might say, well, backward recall is actually a fundamentally different construct. And ultimately, there's some promise for a different intervention target. So let's go fit a 3-factor model to these 9 tasks. So we have the same data, so we have our X1 through X9, and our hypothesis is now the first 3 tasks measure this construct called visual abilities, the second textual abilities, and the third speed abilities. So our first measurement is visual equal tilde. So remember that is measured by X1, 2, 3. The second latent variable is textual, is measured by X4, 5, 6. Third is speed, is measured by 7, 8, 9. And then we look at how well the model fits. And I won't have time to go into model fit in detail. I've uploaded a paper onto the OSF, which gives you a nice introduction, but there are basically 2 ways to think about it. So one is, how much better does my model perform than a really bad reference model? So you want that to be much better. So the CFI is one way to look at that, and you generally want that to be greater than 0.97. The other is, well, given that I fitted my model, what's the average wrongness of my model? And of course, here you want it to be low. So one index to look at is the RMSEA, which you want to be below 0.08. Now, bringing it all together and how to compare a 3-factor model to a 1-factor model. So maybe you have your model where you say, well, there are 3 factors, visual, textual, and speed, which are coded like this as before. But maybe someone comes along and said, well, no, there's just a general ability factor. You don't need all this faffing about with these independent factors. There's actually just a general intelligence factor, which is measured by all 9 tasks. So this model is a bit simpler. So the question now becomes, is the complexity in this model warranted given how much better it explains the data? So we fit this model, and then we fit this model, and then we run our ANOVA. And the question is, given that the 3-factor model is more complicated? Does it significantly outperform the one-factor model? And the answer here is overwhelmingly yes. So the chi-square is much lower, lower is better. The BIC is much lower, the AIC is much lower. So although this three-factor model is more complicated, this complexity is warranted. And the kind of very final example is a full SEM, which is where you have, remember, kind of as said at the beginning, latent variables and regressions. So here we have our same 3 latent variables, because we now decided we needed these 3 latent variables. And we're now looking at the effect of age on each of these outcomes. And we can kind of ignore these for now, but these are basically how strongly are these latent variables correlated. So if we run this model, then we can here look at the regressions. So the visual factor is predicted by age, the textual factor is predicted by age, and the speed factor is predicted by age. And the conclusion you might draw is that age affects textual and speed abilities, but not visual abilities. So you can see here, visual is not, at least not a significant effect, whereas the other 2 are quite strongly significant. And just to show you what this looks like, the 3-factor model, then we go all the way here. So this is our 3-factor model. If we run that here, we get this output, which tells us a little bit about how well the model fits. So this RMSEA is not as low as we would like it to be. So the 3-factor model is better than 1-factor model, but it's certainly not as good as we want it to be. Here we can see our latent variables. So each of these factor loadings are highly significant. So each of these tasks are significantly related to the latent variable. They're strongly correlated with each other. And these are kind of some additional residual variances unexplained by the model. Here we fit our single-factor model. And then here we can combine the 2. And this, again, was the significant likelihood ratio test, which says, yes, the 3-factor model is more complicated, but it does much, much better. And when we fit our full SEM, as the final example, we can look at the 2 components of the model in turn. So first, how do our latent variables work? Well, this, again, still shows that these observed scores are related to the latent factors. And here you see one of the benefits. Now we only have to estimate 3 age effects on the latent factors rather than 9 age effects on each of the individual scores. And we can see there's a strong effect of age on speed and textual, but not on visual. Right. So that's it for me for now. So there's many, many online tutorials. One I uploaded is by Kern and Bauer, who normally give expensive but incredibly good multi-day workshops. And in the pandemic, they decided to make their full Levan in SEM course available online. So I uploaded that for you. There's a nice paper by Shermale Engel et al. From 2003, which walk you through model fit. And me and people in my group have been working on specific applications of SEM for neuroimaging data. So one would be regularized SEM, where you can apply a lasso or ridge penalty. So you can predict a single outcome by many, many tracks or even voxels if you're so inclined. Or dimension reduction specifically for brain imaging data. So we developed a way to reduce data of, say, many regions or many tracts, taking into account the symmetry in the brain. So there's kind of many flexible extensions you can work with SEM. And I think that's it from me. Thank you very much. And I'll take any questions either now or delayed or later by email.
I haven't got any questions come in yet, but I do encourage people to keep typing them. But I have one I want to ask Delia and one I'll ask you afterwards. A question first from Delia from her talk. Have you got any general advice for how complex to make your linear mixed effects model? For example, whether to add random intercepts or random slopes in every model. So how would you advise?
Yeah, so that's a really good question, and one that I think there is, no absolute consensus on yet. So I think a few years ago, a paper came out that talked about the maximal model, and the idea was we should always estimate all possible random intercepts and random slopes to account for everything that's going on. And I think in many ways that's a good idea, because it often is more naturalistic to account for all the possibilities there. But in reality, these models might just not converge. So with the model I showed you, M2, adding more random slopes wouldn't have worked. The models wouldn't have converged there, also because we didn't simulate it to have any of those. But yeah, and that often happens in real life as well. So I think it's a good idea to kind of have a good think about when you're collecting your data, what you might be able to estimate from it. So if you collecting longitudinal data with lots of data points, where you have participants, measured, I don't know, 5 times, you might well be able to estimate random slopes, right? And then, you could pre-register that. But if you're just collecting, say, 2 time points, and then you have a lot of missing data in there, you might just not be able to do it in the end. And then what I would probably do personally, although others might disagree, is pre-register, say, just a random intercept model, and then explore whether I can fit a more complex model.
Great, thank you. And a question for Rod here. So, I mean, SEM is fantastic, and I particularly like the graphical way of thinking about it in terms of what variables are causing other variables. But is there anything that you can't do in SEM, at least for continuous data? Let's assume it's all multivariate normal, etc. But is there anything that, for example, to do with random slopes and intercepts that you can't do with SEM?
I mean, there are 2 things. So one common stereotype, which is justified to some degree, is that SEM is a larger sample method. So ideally, it works with kind of having, say, at least 100 people, ideally more. Then again, I would also defend the position that that's true for correlations and t-tests also. Mm-hmm. There's also a question about when to use, for instance, SEM versus LME. Now, there's kind of wonderful niche papers, if you can't fall asleep, which show the formal equivalence between the 2 techniques. So under the hood, you can rewrite one into another model. However, something being formally equivalent doesn't mean it's practically equivalent. And there are types of models where an LME is simply easier to fit. They are often less finicky, so they're slightly more likely to converge. And there are types of things that LMEs do easier than standard SEM. So one example would be if I measure every individual, say, 100 times, and the intervals differ a little bit. So an SEM does really well if you have T1, T2, T3, and everyone is exactly the same. A linear mixed effect model will have a much easier time if you measure one person at 9 a.m. and another person at 9:07, etc. So if the time intervals vary. So that's one example where I can do it equivalently in SEM, but it would ruin my day. So they're kind of pragmatic settings where an LME would be a bit easier.
Brilliant. Thank you.
Sorry, if I could.
Yeah.
So I think the other kind of trade-off you have is with missing data. So in a while ago, it was actually really hard to account for missing data well in mixed models. There's now been a lot of development on that front, so it's getting much easier. But definitely, in Lavaan, it's super easy to account for missing data using full information, maximum likelihood, and things like that. And that's quite straightforward. So if you know that you've got complex missing data patterns, that might be a consideration.
Yeah. So taking account all the complex dependencies between the variables in order to deal with missing data. And that's a whole another kettle of fish we haven't had a chance to talk about today. But yes, maybe we can find some literature for dealing with missing data and data wrangling more generally that we can post on the OSF site. If there are no more questions, I think we'll go ahead with the final talk. And then again, if there's any questions for any speaker, please do type them at any point, and we'll, if we have time, we'll come back to them. Okay. So I'll give the final talk about Bayesian statistics. And I'm hoping you can see my slides. I hope one of the other speakers will interrupt me if they can't see the slides. Yeah, so as you're probably aware, there's a theoretical division between classical or frequentist and Bayesian approaches to statistical inference. And I'm sure you're aware that the classical p-value used in frequentist statistics is the likelihood of getting a statistic which is derived from the data, D, of a certain size or larger, given that the null hypothesis, which we're going to call H0, is true. And that null hypothesis states the effect size is exactly 0. So it's the probability of getting the statistic from the data given H0. Another way to make inference is to use what's called the Bayes factor. And this quantifies the relative evidence for one hypothesis versus another, such as H1, the alternate hypothesis, against our null hypothesis H0. And it is simply the ratio of 2 likelihoods. So the likelihood of getting D given H1 relative to getting D given H0. And that is BF10. So the 10 refers to the ratio for H1 over H0. Although to calculate this quantity, we will need to specify some priors on the parameters that characterize both hypotheses. And I'll come back to that important point in a moment. But first, why we want to choose one over the other. And this is taken from a nice paper by Dinesh in 2011, talking about the problems of classical inference, or conversely, some of the advantages of going Bayesian. So first, you're probably aware that a non-significant p-value, so a p-value greater than our nominal alpha of, say, 5%, does not mean there is no effect. So absence of evidence is not evidence of absence. But with Bayes factors, we can quantify the evidence for the null. So BF01 is just the reciprocal of BF10 that I showed you in the previous slide. Another issue is that with frequentist statistics, a significant p-value can be found for effect sizes that are tiny or implausible. So, for example, you might be measuring human reaction times and find a difference between two conditions of, say, 5 milliseconds, when you were expecting a difference of 50 milliseconds, so 10 times more. That 5 millisecond difference could be significant, but if you take a Bayesian approach and you assume that the null hypothesis would assume effect around 0, small values around 0, and the alternative, you're expecting effects around 50 milliseconds, then you can actually find a Bayes factor favoring the null hypothesis, because if you're expecting 50 milliseconds, then 5 milliseconds is unlikely. And in other words, Bayes factors make reference to the likely effect sizes. Another issue with classical inference is that the more tests you perform, the more likely you are to have a false positive or a type 1 error when you declare when p is less than 0.05, but actually h0 is true. Well, with Bayes factors, arguably you can address this in different ways. So if you have the same hypothesis being tested on multiple data sets, you can simply combine the Bayes factors across data sets, as I'll talk about in a moment. Or if you have multiple different hypotheses on the same data set, you can actually adjust your prior to take into account the family of tests you're doing and the possible correlation between them. But you don't need to do any post hoc adjustment. And finally, an important aspect, at least of the Nyman-Pearson interpretation of classical inference, is that you must specify the sample size or your stopping rule in advance. So you can't look at your data, find that p is 0.06, let's say, and decide to just collect a few more observations just to try and get you below your nominal alpha value. That's not strictly correct in the Nyman-Pearson interpretation, but it is possible with Bayes factors. The main reason is that if the null hypothesis is true, the distribution of p-values across multiple experiments or data sets is actually uniform. So you're equally likely to get any p-value. Only 5% of the time will that be less than 0.05, but you will get any value. Whereas with Bayes factors, if you add more data and the null hypothesis is true, then the Bayes factor for the null will just keep increasing. And so you can keep, with Bayes factors, you can collect the data, look at your Bayes factor, and if it's reached your criterion that you specify in advance, you can actually stop collecting data. And this allows for much more efficient designs, such as sequential designs, which I'll finish my talk with, because I think they're important ways to collect data more efficiently. So if we want to make a decision based on a Bayes factor, we have to have some convention. And here's a convention suggested by Wagemakers et al. So basically, a Bayes factor of between 3 and 10 for the alternative is moderate evidence for H1. More than 10 is very strong evidence. Now, this is like 5% for the alpha value in classical statistics is an issue for scientists to agree on some convention. Most journals these days require a Bayes factor of at least 6 or often 10, as you might find in, for example, registered reports. In our own work, we tend to require a value of 10 for BF10 and a value of 6 for BF01. And I'll explain the reason for the different thresholds in the last part of this talk. But this is really for the field as a whole to agree on. Now, the important point of Bayesian inference, or using Bayes factors, is the role of priors, which is also the most controversial part of Bayesian inference. Because we need to calculate this likelihood of the statistic or the data D given some hypothesis. And for that, we need to integrate over or take out all possible values of the parameters theta. So theta are the parameters. And so P theta H are the priors on those parameters according to a particular hypothesis, either H1 or H0. To make this more concrete, let's take a simple two-sample t-test where there are actually two parameters. For H1, the two parameters theta1 and theta2 are the mean, mu, and the standard deviation, sigma, of the error. Under H0, which assumes that the mean is 0, there's only one parameter, which is, again, sigma for the standard deviation of the error. So these need priors. How do you specify them? Well, subjective Bayesians would propose some priors based on a particular theory or even previous data. And of course, this is the most controversial part because different scientists can have different priors and they'll get different Bayes factors or make different inferences. And this is actually partly why the frequentist approach was developed by Fisher and Nyman Pearson in the 20s and 30s, was to try and make the inference more objective and not require priors. On the other hand, having priors does give all the benefits I showed earlier in this talk for using Bayes factor. What you can't do, of course, is choose your priors until you get the Bayes factor you want. It's very important to have principled reasons for your priors, and ideally you pre-register your choice of priors or write a register report to make sure that reviewers agree with your choice of priors before you collect any data, so that you can't be accused of switching the priors later on. But another approach is to take the more objective Bayesian approach, which is to have some minimal or default set of priors on certain statistical tests that we as a community agree are plausible. So there's less choice here. You just take the default for that test. And one example of this are the JZS priors, often used in t-tests and linear regression, which I'll show in a moment. And they are implemented in the Bayes factor package for R. What happens here is you specify the alternative hypothesis H1 in terms of the effect size delta, the mean divided by the standard deviation squared. And this, if you follow through the maths, it gives you, there are some principled arguments for adopting what's called a Cauchy prior on the effect size, or more precisely, scalar R times a Cauchy. So a Cauchy is actually just a slightly narrower version of the normal distribution, and this derives from assuming a normal distribution on the variance of a normal distribution. So it comes from principal mathematical approach. R is a factor you can choose. For the sigma squared, you can adopt a Jeffreys prior, which says that basically the probability of a particular sigma squared is inversely related to the size of sigma squared. And if you put those together, you get the Jeffreys, Zellner, Zio, or JZS priors, which are now very common in many statistical packages. The default R value, this scalar, is half of √2, but if you want to, you can increase this if you expect the effect size to be larger. But this is chosen to be typical for typical experiments that are done. Once you've used these priors, you can estimate quite quickly, and you can get a Bayes factor, which I'll show you in a moment, and also plot what's called the credible interval for a parameter, similar to a confidence interval. So at this point, I will switch to our studio. So I'm going to use the same data that Delia showed. You need to have these two new libraries here, Bayes factor, which I'll show now, and then in a moment I'll show BRMS. You load the data, and I'll do it again, but I've done that. Then we have the paired t-test that Delia showed. This is the equation that she used, and this is just the Bayesian version. With the paired t-test, unfortunately, we can't express this in terms of the formula. We just pass this function t-test bf with two arguments, child and adolescent. So I've just selected these from the data frame. And if I run that, you can find an absolutely enormous 10 to the 15 Bayes factor for the alternate. So not very realistic data, but data that shows a massive effect of massive difference between the two ages of each person. We can also, if we want, plot some samples from the posterior. For example, the mean mu. This may take a while because the swap card is eating up most of my CPU, but this will give us a distribution over multiple samples of the mu, and it will be about sent about -9, I think it was a difference that Delia showed when she did this. Okay, I'm going to stop that because I don't know why that is taking so long, but that would give a histogram of values for a posterior distribution for mu. And you can try this yourself. This same code is available on the OSF site. Delia also showed a sort of repeated measures DLM using the LMER function. We can do the same thing with the LMBF function. So if we want to get the base factor for the main effect of participant age, what we do is we specify two models, similar to what Roger was showing, where the first model here, the first line here is exactly the same formula as Delia used. And then we specify another model without the main effect of age. Then we, having fit those, we can calculate the BF10 as the ratio of the likelihoods of the model with age and without age. And again, that takes typically about 30 seconds to run. It's a bit slow. Because of SopGuard eating most of my CPU, I'll probably just show you the results earlier. And again, we get a massive base factor for the main effect of age. But here's something we couldn't do with classical statistics. Do the same thing now for a model with and without the fixed effect of face emotion, which you may remember Delia showed was not significant in a classical analysis. So now we can calculate the base factor, BF01. If we specify it as in this way, then BF01 is 1 over that. So the null here that there's no effect of face emotion. And with this, we get a base factor of about 68. So really strong evidence that there is no effect of face emotion in these data, consistent with the non-significant effect that Delia found. But now we can actually make an inference about this null result. Okay, I've got to switch back to PowerPoint now. Just to illustrate very quickly, another package you can use, which is more powerful for the power user. It can handle generalized linear models. So you can add linking functions to, for example, do logistic regression. And this is the BRMS package in R. It uses the same formula notation that Delia illustrated for LMER. But you can add, as I said, additional linking functions to generalize the model. And most importantly, you can specify any prior you want for any parameter, well, that has a known distribution. And of course, this is where there's a lot of debate about the best priors for certain types of models, such as logistic regression. And here's a website where you can read about good choices for priors. It's very important that you scale your variables so that the parameters that are estimated are the same scale as the priors you put in them. That's a common error. This does take a long time to run, however. It uses Markov chain Monte Carlo sampling, so it takes a long time, and there are issues to do with convergence. You need to run it a lot, often, to get a clear answer. And for that reason, again, I won't show you it running live. I'll just show you how you would run it. This takes almost a day for these data because they're very large data. But what you would do is first specify your priors. Here, class B refers to basically all the parameters in the model, in addition to the intercept here. And I'm putting unit normal priors on these. But you could put a Cauchy or anything you want on these individual parameters if you so wanted. I'm also going to scale the age and dependent variables using Z-scoring, just so that they match the normal distribution prior here. And then this is the call to BRM. And this is the same formula that Delia finished with, where we have random intercept and slope for participant age, and random intercept for face identity, the stimulus, if you like. And here are some other arguments that you can read about if you do help on this BRM function. But if you run this, and again, I'll just load up one that was run earlier. Basically, we can do the same thing that I showed you earlier. We can compare models with and without a particular fixed effect. So in this first line here, we're taking the full model, and this is just shorthand for saying remove the effect of age. So now we've got a model without age. We calculate the base factor for these two models. And if you do that, again, not surprisingly, there's a massive effect of age. And we can do the same thing with and without emotion. And here we found a strong high base factor for there being no effect of emotion. Okay, in the last few minutes, I just wanted to show how you can use Bayes factors to have more efficient experimental designs, namely sequential designs. And this is described in this paper by Schoenbrot and Wagemakers, which is on the OSF site if you want to read it. Let's take a traditional design where you specify in advance how many participants you're going to test or how many observations you're going to make, the fixed end design. But we're still using Bayes factors here. So the red line is the probability of getting a Bayes factor. The blue line is the probability of getting a Bayes factor greater than 10 for the alternative. The red line is the probability of getting a Bayes factor greater than 6 for the null, or less than a 6 for 1, 0. And this horizontal line here is an 8% probability. And what we can then calculate by simulation is if the effect size is 0.5, so this is the H1 is true, then to get 80% probability of finding a Bayes factor greater than 10, we need about 72 participants. And very, very rarely we get misleading evidence for the alternative, for the null here. Or if the null is true, if we want to get a bit similar but not the same as power, but similar idea, then we need 232 participants to get a Bayes factor greater than 6 for the null. This is why it's quite hard to get, with these priors, evidence for the null. And this is the hypothetical cost for an fMRI experiment. Just to keep these figures in mind, I'll show the comparable figures with other designs. I should say that all these simulations are on this link here, and they're done by my student Alex Quent. So with a sequential design rather than a fixed end design, we start with a minimal sample, for example 10, and then we add batches of data, say every 5 participants, until we reach our criterion for either the alternative or the null. So here's some simulations of multiple different experiments. The purple lines are, this is when the null hypothesis is true. So most of the time, after a certain number of participants on the x-axis, we exceed our criterion of Bayes factor greater than 6 for the null. But occasionally in these red lines, we actually get the opposite result of a false positive, if you like, for evidence for the alternative. But most of the time, we converge. And if we then run this for the case where there is no effect, you can see a histogram of how often we stop the experiment at different sample sizes. And then there's, in red here, there's a small case of stopping due to false positives. Sorry, excuse my phone going off. And then this is the case where we simulate an effect of 0.5. So this is the histogram of when we stop with a Bayes factor greater than 10 for the alternate. And if we look at the numbers, so the 2 rows are the same as in the previous table, now we are running indefinitely. So we're going until we exceed our criteria. So we always find evidence, or nearly always. And so we need 170 subjects here to be really confident of finding Bayes factor greater than 10 for the alternate when it's true. But we need to run at least 3,000 people if we want to be confident that the null is true. So that would be a sequential design where you just keep testing until you exceed your criteria. But often we have a practical limit on how many observations we can make. So we can set an upper limit, say, let's stop after 100 participants, no matter what. So there will be cases where we don't have strong evidence either way. And now look at the numbers here. So we still have a really high chance, 98% chance in this scenario of effect size of 0.5, of finding a Bayes factor greater than 10 for that if we definitely stop after 100. On average, we stop after only 40. For the when the null is true, we have a situation of about 80% like before. Most of the time, we will find a Bayes factor greater than 6 for the null when the null is true. The price we pay for this stopping rule and stopping it is that we have a higher rate of misleading evidence when we would get the wrong result. But again, on average, we're down to 60 participants. So this is the massive saving in efficiency at the cost of more misleading evidence. So we can decide on whatever we want to cap that misleading evidence at. But putting them all together, the basic point is that for sort of proving the null with these priors, we might need to spend £130,000 in an fMRI experiment to test 232 participants to have a reasonable chance of supporting the null. Whereas if we take a sequential max-end design, we've cut the cost by a third. So it's much more efficient at the cost of slightly more chance of misleading evidence. So this is up to you to take out this trade-off, but it can be a much more efficient way to run experiments. So the references I've used today are all here. And again, PDFs of these are available on the OSF site. And that is me done. So if I just stop the sharing and then go back to StreamYard. Okay. I'm looking at the questions that have come through. Question, what type of sampler does Bayes factor use under the hood? I would suggest that you do help on the relevant function, and it will tell you what the sampler it's using. How many iterations does it take to compute reliable estimates? That depends a lot on the model, the complexity of the model. But yes, you sometimes need tens of thousands or more. Again, there are defaults for the Bayes factor functions that you can change or increase if you want to. For the BMS functions, yeah, it's really important to have lots of iterations, which might take a long time to run. Are priors other than JSZ using the Bayes inversions of univariate statistical test? Well, there certainly are, in theory, lots of different priors you could use even for a basic t-test. The JSZ prior has become kind of quite common. It's used, for example, in the JASP software, which is another package you could use. And it's as implemented also in R by Ruder and colleagues. So yes, it is becoming more conventional, but you could, as I said, use any prior you want with BRMS if you so choose. But I think that's the approach I talked about of being, if you're worried about the results depending a lot on your priors, then stick with some default priors, some minimal priors that make minimal assumptions that the field as a whole agrees to use, and then you can't be accused of changing your priors, so not post hoc.
Can I jump in there, Rick?
Go ahead, Simon.
Obviously, another strong contender for a choice of prior is a published paper you're trying to replicate. So,
yes.
So if you use the consensus of the field to inform what the field believes, so say something from a meta-analysis might give you a prior from that meta-analysis for what the field believes, and then you would be doing more of a confirmatory analysis. So does your confirmatory study concur or disagree with a meta-analysis from the field? So that it isn't always just use an objective, non-informative prior. There are good reasons to use very subjective priors in certain situations.
Yeah, and so that's the approach we take when we do multiple experiments. We often use the posterior for one experiment as a prior on the effect size for the next experiment. It's equivalent to combining all data in the end, but it's a nice way of thinking about how you approach the inference, to use data to inform the priors for the next experiment. Right, I don't know whether there are any more questions coming.
Rick, there was one question on the slides for the workshop. So the resources are all on OSF, and the slides, I think, shortly will be. I think Delia and Simon will undoubtedly be happy to add their slides to the OSF resource.
So if there are no more questions, yeah, we will probably update the OSF as we go along, but they're certainly available there now, or should be very soon. If there are no more questions, then I'd just like to take this opportunity to thank the other four speakers, because they've done this out of the kindness of their hearts to get their time to prepare the materials and give their talks. So we're very grateful to all four of you. Thank you so much for devoting your time, and I hope that within reason, we'd be willing to take any more questions that you might have after the session finishes if you want to contact us via the BNA website or even by email. Obviously, but we might also point to other courses that are available. And I know several of us give longer courses, and I'm sorry this has been a bit condensed, but we wanted to give you a flavour really of from the very beginning to the sort of more power user opportunities that are available in R. And if you want to fill in the gaps in between, there's lots of material online. Right. Well, I think we should close the session then, but thanks again to all that attended. If there is anyone left, I don't know. And thanks to all the speakers again for fantastic talks. And enjoy the rest of the conference.